In this calculus lecture, we're going to explain finding the area between two curves. Now, before we get into the specific example I have, where we have more of a parabolic type of function, and then we just have a simple linear function, let's actually define how we find the area between two curves. Now, for this lesson, you need to have some understanding of integration. How do we find integrals? How do we find the area of a curve in general by using a definite interval of some value b to some value a. So here I have the formula for the area between two curves. We will define that as a sub 2c, area between two curves. Makes sense, right? So the area between two curves is going to be equal to the area of the top minus the area of the bottom. Now, what does that mean? Take this little function I have here. So I have some parabolic function with the solid line, right? That would be like negative x squared. This is negative x squared plus some value c, right? And then I have a function here which is just y equals some constant of like 2, for example. Okay, so what this is saying, if I want to find the area of their intersections, aka the area right in here, right? If I want to find this area, right? If I take the integral of negative x squared plus c, it's going to assume it wants to find the volume, or sorry, the area of the entire section here with respect to the x-axis. So it's going to, when you find the integral of the definite range between this value, or sorry, of this value and this value, it finds it with respect to the x-axis. Makes sense, right? So then we take, let's say we have some function, which I'll use in a dotted line, right? When I take the integral of, and sorry, I'll just erase this here to make it more simple, with respect to this here, if I find the integral from the same range, right, it's going to find the area here. So when you put it all together, right, and I'll draw again our parabolic function and what that's finding. So if we have this section minus this section, we get our original section that we were looking to find. So we just subtract it out. And we have the range of which we're trying to find here. So quite simple. We can find the area between that curve as such. So another way would be to set the, and now this is another way that we can do this, which we will explain later, is you can actually set these equal to each other and then find their intersection points, and from their intersection points you can find, you don't have to do any subtracting out. Okay, so let's take, for example, the function y equals 1/2 x to the third minus x minus 2. Okay, that's that little parabolic looking thing, little snake function. So we have that function, and then we have an intersecting function of just a linear x minus 2. What this does is we have two regions that we want to find. So we want to find this region, and we also want to find this region. So I've sketched out, bolded the sections we want to find. So how can we find this using integrals? Well, we first have to define the intersection points. So we know that there's two regions, right, where we flip from the top, a function being on the top to the function being on the bottom. So let's take this interval for, we can actually just split this up into two integrals here. So here we have at -2, the line begins to intersect, and then it collapses at 0. So we're going to find the derivative, or sorry, the integral from 2 to 0 of our top function. So that's, our top function is 1/2 x third minus x to the -2nd. Okay. So we have that. Right, that's going to find the area, all of the area in this section here with this function. So we have all of that. and then we're going to subtract it by the integral of 0, -2 of x minus 2. Okay, quite simple. Or sorry, this is flipped. Because if you're on the top, your top function is your top function. This is our bottom function here, sorry. Our top function is actually the linear function here because we're below the x-axis, so you kind of have to flip it 180. Hopefully that makes a little bit of sense, but you can see x minus 2, geez, what a critical mistake to make. That would make you lose points. So we have this function which is graphing out the entire section, right? And this starts to make a little more sense. I apologize for the mistake. It's going to graph out the whole function with respect to the x-axis, and then we're going to subtract the parabolic section, which does not include the shaded section, right? So we're kind of cutting that out, right? So if I were to draw this on a graph, what the integral of our linear function is finding is this section here, right? We then subtract the parabolic region, and that will help us find, and sorry, this is going to look awful, it's going to cut out the part of the parabolic function, right? Because the parabolic function is seeing this. The parabolic function, so it's seeing, let's say, the parabolic region is not seeing this here, it's seeing all of this area. So we just subtract it out, and we're left with just the part by the linear function. So hopefully that makes sense. I probably did an insanely terrible job at explaining that, and on top of that I also made a little mistake. So let us now do the math here. So the integral of the top minus the integral of the bottom, 1/2 x to the third minus x minus 2. So let's just find that there. Let me make sure you guys can see, so I'm going to actually bring this down a little bit. The integral here is, so x, 1/2 x squared. Take the derivative of that, you get x, minus 2x, and then we're going to note by this notation that we're finding, we're going to evaluate it from the interval 0 to -2. We'll call this this function big F of x. So we're going to find f of 0. To find the area of that curve, we're going to find f of 0, the top, or sorry, the b, and then minus f of -2, which is a. So let's just do some math here. Plug it into a calculator. So 1/2. We know that 0 will obviously be 0, so we don't need to find that. Because any x times 0 is 0, and we don't have any constants. So 1/2 to the -2 squared minus 2 -2. So we actually get 6 here. So our total area is -6. Alrighty, so we then want to subtract that by this function evaluated at the interval. We're finding the integral of that. We'll call this g of x. G of x here. And this is going to be equal to, and now remember your power rule for integrals that states, okay, this would be over 4. So this is 1/8 x to the 4th minus 1/2 x squared minus 2x. And we're evaluating this in the definite range of 0 to -2. Okay, so we have that defined there. Now we just plug and chug to find g of 0. We know g of 0 to be 0. And then I will simply do some plugging and chugging for us because we're subtracting it by g of -2. And that's going to equal some value. So 1/8 -2 to the 4th minus 1/2 x squared, so that's -2 squared minus 2 to the -2. And that evaluated is -4, so this function here, this should be -6. Oh, it is -6, and this is -4. So we found the area of each function respectively. Our linear function is giving us an area of -6 with respect to the x-axis, right? That makes sense because we're on the lower half of the graph quadrants, right? -6 units squared. Okay, and then for our parabolic function, it actually turns out to be a nice whole number of -4. So to find the area, we just subtract the two, right? So it's going to be, so for the function, for the area of this curve, we're going to call this a of 1, right? Because we also need to find a of 2. So a of 1 is -6 minus -4. So we have a double negative, we add, area 1 is equal to -2. All right, so the area of this shaded region is -2. Hopefully that makes sense. Now, I challenge you to find the area of the second one. I'll actually give you the interval. It starts at 0, ends at 2. So now it can't actually turn out where you have to actually find where they intersect to help you find the interval there, but in this case, not so much. Okay, so let's go through this here. Remember, it's area of the top minus area of the bottom. So our top function actually turns out to be the parabolic function this time. So we are going to evaluate this from 0 to 2, 1/2 x to the third minus x minus 2. And then we're going to take this integral and we're going to subtract it by the bottom integral. So we're going to put our integrand of 0 to 2, x minus 2. So we're just finding the difference between the two areas, and that is expressed by the integral notation here. So let's actually find the integral. We said that the integral was 1/8 x to the fourth minus 1/2 x minus 2x, evaluated from 0 to 2. Okay, and then we're going to subtract this by, and this would be 1/2 x. And sorry, I'm going to put, it's going to get messy, but that's okay. Who cares? Minus 2x. And then we're finding that with respect to 0. Okay, so we have our functions here now. We just evaluate. We'll call this function f of x. Big F of x, we'll call this one g of x. Let me just make sure you guys are able to see. Oh, it's going to be a little cut off. I apologize. Let me scoot this over here. So g of x, big G of x, big F of x. Let's find the interval range. So to find the area, we have to find f of 2, and we subtract that by f of 0. Okay, so let me see here. So we know f of 0, of course, is going to be 0 again. We find f of 2 to be -4. So -4 minus 0, that's just -4. Okay, so now let's go to our other function here. We're going to say g of 2 minus big G of 0 is equal to some value, which is the area. So g of 2, let's find that. We know g of 0 to be 0. G of 2 is -2, so -2 minus 0 is just -2. Okay, so now we have to plug it into what we said our general formula was to find the area of this curve, and I will move us back over. Sorry, lots of moving here. The area of the second interval, we can find that by taking the area of the top minus the area of the bottom. So let's go ahead and do that. The top function in this case is going to be our parabolic function, and that is described by this, and we said that is -4. Okay, we have our bottom function, which is the one that's closer to the x-axis. That's our linear function, and we said that the area of that with respect to the x-axis is -2, and we're subtracting by a negative once again, right? So area 2 is -4 minus -2. Minusing a negative is more like adding, so we're going to call this -2 as well. So we actually find that the area between these two curves is -2 respectively. Okay, so what does that say about the total area? I'm asking you about the total area of the intersection between these two at those given points. So between these two regions, what is the total area? Well, this one's negative 2. And we can just add these. A1 plus A2, negative 4, right? This area is negative 2. That area is negative 2. So we get a total area of negative 4. I hope you guys enjoyed and found this video helpful. If you did, please drop a like. Hopefully I explained things in a relatively good way, but if you have any critiques to the way of which I teach, I would love to hear them. Put them down in the comments below. Have a wonderful day.